Welcome back, folks. Before we get too much into the more complex chemistry in the cell and use that to build up some understanding of cellular processes and structure and function kind of things, I want to take us back to looking at some just very basic but very, very important principles regarding water. So I'm not going to get into water in excruciating detail. I just picked a couple of topics here which, in my experience, is worth reviewing because of the difficulty it presents for some students. So here's a water molecule, and one of the things that hopefully you take from General Biology 1 is that water is an excellent molecule on which to base life, and that becomes evident that emerges, if you like, out of the polar nature of the molecule. So the polarity in a water molecule arises from two features. And even here there's a nice structure-function relationship to think about. So first of all, there's an unequal distribution of electrons across the bond that forms between the oxygen and the hydrogen atoms in the water molecule. So there's two of those bonds, and so the oxygen at one end of the molecule is highly electronegative relative to the hydrogen at the other end of the bonds, which form the other ends of the molecule. And so the electronegative oxygen draws the electrons towards it, and that results in a partial negative charge at the oxygen end of the molecule, if you like. And so we have that aspect of polarity, and we'd only get that polarity because the molecule is bent, and so the bond angle between the oxygen and the two hydrogens here is close to 105 degrees, and so the bent nature, the nonlinear nature of the molecule and the relative electronegativity of oxygen compared to hydrogen gives us this charge distribution across the molecule, wherein the oxygen is slightly negatively charged and the hydrogens are slightly positively charged. Now remember, these aren't complete charges. This is not an ionized molecule, so this is not a complete negative charge. That's not the complete acquisition of an electron, and it's not a complete positive charge on the hydrogens. That's not a complete loss of the electron. If you looked at a density map of where these electrons would be in terms of orbiting these atoms, they would just spend more time closer to the oxygen than they would closer to the hydrogen, and so these two features give us the polar nature of water. And so that leads to an interesting property of water, and that is that water molecules are attracted to one another and to other polar molecules or polar parts of molecules. So the electronegative oxygen will be attracted to the electropositive hydrogen of another water molecule, and such an attraction is called a hydrogen bond, and you find this all over the place in biology. I think it's one of the most important bonds to be familiar with. So this is a weak electrostatic interaction between an electronegative part of a molecule and an electropositive part of a molecule. One's called the electron donor, one's called the electron acceptor, and this gives us a hydrogen bond. These are about 1/10 as strong as a covalent bond. So the polarity in the water molecule leads to a number of really important biological consequences, and this has obviously some important things for us to. This leads to some important things for us to think about in terms of cell biology. So if you think about liquid water, it's characterized by this extensive network of hydrogen bonded molecules. So the network of water in a cell, all of those molecules are hydrogen bonded together, and that produces a phenomenon known as cohesion. Now when water associates with other polar molecules, that's known as adhesion. All of this cohesion in water gives water a high specific heat, and that gives it the ability to stabilize temperature very effectively. So when we think about specific heat, this is the amount of heat a substance must absorb to increase in temperature by 1 degree Celsius. So the specific heat of water is 1 calorie per gram. That means that if you want to raise a gram of water by 1 degree Celsius, you've got to put a calorie of heat energy in it. Now that is higher than most liquids, which makes water an excellent solvent on which to base life. It means that bodies of water don't heat up quickly, they don't heat up to very high temperatures, and they don't cool down quickly, and they don't drop to very low temperatures. We obviously have some ranges in which life can live, and water helps us keep our bodies and our ecosystems within those ranges. So is what happens is when you heat a volume of water compared to a volume of liquid which doesn't have extensive hydrogen bonding, in the water the first thing that happens is the hydrogen bonds start to break and you start to get vaporization, whereas in other liquids you actually increase the liquid of the temperature of the liquid, and so the heat that would normally go into raising the temperature of the actual liquid, the molecules themselves, in water goes into the hydrogen bonds, and then when you put energy into bonds, as you know, they break, and then we have vaporization, we have evaporation of water. And so is what we end up with is a situation where if you heat water, its temperature raises pretty slowly, and that protects organisms and ecosystems from dramatic, rapid changes in temperature. So without that characteristic, life would be very difficult, which is why people tend to look for water as a sign of life on other planets. They're either looking for water or some new kind of solvent on which to base life. Let's finish up here talking about water's role as a solvent, and this also arises because of the polar nature of the molecule. Remember, the oxygen is electronegative and the hydrogen is electropositive. So a solvent is a fluid which can dissolve another substance, and that's called the solute. And so because of its polarity, water is able to dissolve a large number of solutes which are either completely charged or have regions of polarity if they're neutral. So there are many things which can dissolve in water, and that's obviously important because you need to dissolve wastes and you need to move substances around inside cells and inside bodies, and you couldn't really do that unless you could dissolve them in fluids. If you've taken general biology, you've heard me talk about how it wouldn't be much fun to be passing crystals of uric acid. Rather, we dissolve it and expel the molecule in that way. So the molecules which dissolve in water freely are said to be hydrophilic, and substances that are oily are hydrophobic, and they tend to repel water, and when they repel water they tend to stick together. So hydrophobic things tend to stick together. That's obviously the basis of forming cell membranes. And so here on the left we're looking at a positively charged sodium ion, obviously interacting with the oxygen of these four water molecules, and then on the right the chlorine ion, Cl- interacting with the positively charged hydrogens of the water molecules. And so the chlorine and the sodium don't go back together to form the crystalline lattice that you're familiar with in sodium chloride, because these hydration shells prevent the sodium and the chlorine coming back together. So the water is surrounding the chlorine and the sodium in a hydration shell, and that's more stable. And for reasons of entropy and things like that, the sodium and the chlorine don't come back together. This is a more stable situation. So those are just a few things about water, and I hope you remember a lot more about water from general biology. I'll see you next time when we're going to start looking at lipid bilayers and just again reviewing some basic stuff about lipid bilayers. I'll see you next time.